If humanity is to overcome the crushing brutality and omnipresent likelihood of eventual human extinction set by Mother Nature, then unequivocally evolving towards a multi-planetary species is the only way to protect the future of the human race. Since the dawn of time, every human blessed to be born has had the luxury and pleasure of experiencing life's many virtues and sufferings on this delightful floating rock suspended effortlessly in our solar system that we call our shelter and home. And yet, if Armageddon occurred today, humanity would be massively unequipped to survive, likely perishing as a species. Every emotion, personal milestone, and interpersonal experience shaping your life story, making you undeniably and uniquely you, would vanish in a millisecond. Thus begging the question, how can humanity afford to procrastinate on advancing our spacefaring technologies for future generations to inherit, when, despite our denial, the scary yet eventual truth is that one day our planet will die, and we along with it, if we are unable to escape into the cosmos and colonize planets to begin anew. To whoever is listening right now out there in this beautiful universe, let's pause, take a deep breath, and explore the reasoning behind why space colonization is essential for human survival and the inevitable challenges we will face in our triumphant attempt at becoming a multi-planetary species. Before we begin our space colonization journey together, let's first set the record straight. Astronomers estimate that the Sun has 7 to 8 billion years left before it sputters out and dies. In 5 billion years' time, the hydrogen in the Sun will run out, transitioning the Sun into a red giant, which is defined as a luminous giant star of low or intermediate mass in a late phase of stellar evolution. At this point, the Sun's fusion will stop, which occurs when two atoms slam together to form a heavier atom, and the helium core will begin to compress under gravity, leading to a dramatic rise in the Sun's temperature. As the Sun's heat rises, the outer plasma layer of the Sun is projected to expand up to 200 times its original size, in the process engulfing Mercury, Venus, Earth, and Mars in order to reach a new equilibrium state. Even more alarming than the Sun swallowing Earth up whole like a ghost from Pac-Man, in roughly 1.3 billion years from now, humans will not be able to physiologically survive on Earth due to sustained hot and humid conditions, in which humans can no longer cool off by sweating. Humans, and all complex life for that matter, are super needy, and a fever of only 6 degrees Fahrenheit, or 3.3 degrees Celsius, is life-threatening. Furthermore, in about 2 billion years, the oceans will likely evaporate when the Sun's luminosity is nearly 20% more than it is now. Some life may survive to this point, like the extremophiles that live near hydrothermal vents in the ocean floor, but not humans. For as good of a run as our planet has had over the last 4.5 billion years, like all things in life, what goes up must come down, making it imperative for the human race to escape our solar system. For our survival, we must complete the childhood fantasies of every Star Wars and Star Trek movie enthusiast alike, and explore the far-reaching galaxies of the universe for space colonization. Let's first begin with some facts. Space colonization is defined as the settlement or colonization of outer space and astronomical bodies. To date, no permanent space settlement other than temporary space habitats have been established, nor has any extraterrestrial territory or land been internationally claimed. The mere construction of an extraterrestrial settlement with the needed infrastructure presents daunting technological, economic, and social challenges. The environment in space is very hostile to human life and not readily accessible, particularly for maintenance and supply. It would involve much advancement of current primitive technologies, such as controlled ecological life support systems. Currently, the dominant private launch provider SpaceX has been at the forefront of planning space colonization on Mars, though having not reached the development stage beyond launch and landing systems. With the high cost of orbital spaceflight, around $1,400 per kilogram to low Earth orbit, a space settlement would currently be massively expensive. But ongoing processes in reusable launch systems, possibly reaching $20 per kilogram to orbit, and creating automated manufacturing and construction techniques aim to change that. There are many proponents in favor of space colonization that insist that its accomplishment will secure the survival of human civilization, give humans access to the vast resources in space, promote territorial expansion with fewer negative consequences, alleviate overpopulation and resource demand, and create an enormous amount of utility via the utilitarian perspective. We're going to discuss each further, but before we do, let's first talk about some opinions from a few pundits on our chances of survival. Well, theoretical physicist and cosmologist Stephen Hawking stated in 2001 that the human race would be extinct within the next 1,000 years unless colonies could be established in space. Lewis J. Hall Jr., formerly of the United States Department of State, wrote that the colonization of space will protect humanity in the event of global nuclear warfare. On the other hand, J. Richard Gott estimated that the human race could survive for another 7.8 million years, but it is not likely to ever colonize other planets. A final insight comes from a group of researchers in 2019 that pondered the long-term trajectory of human civilization and determined a 4-step process for space exploration. At first, space colonies could be established at various habitable locations, be it in outer space or on celestial bodies away from Earth, and allowed to remain temporarily dependent on support from Earth. In the second step, these colonies could gradually become self-sufficient, enabling them to survive if or when the mother civilization on Earth fails or dies. In the third step, the colonies could then develop and expand their habitation by themselves on their space stations or celestial bodies, for example, via terraforming, which involves transforming a planet to resemble the Earth and support human life. And lastly, in the fourth step, the colonies could self-replicate and establish new colonies further into space, a process that could then repeat itself and continue at an exponential rate throughout the cosmos. However, this astronomical trajectory may not be a lasting one, as it will most likely be interrupted and eventually decline due to resource depletion or straining competition between various human factions, bringing about some Star Wars scenarios. Importantly, resources in space, both in materials and energy, are enormous. The solar system has enough material and energy to support anywhere from several thousand to over 1 billion times that of current Earth-based human population, mostly from the sun itself. Asteroid mining will likely be a key player in space colonization. Water and materials to make structures and shielding can be easily found in asteroids. Instead of resupplying Earth, mining and fuel stations need to be established on asteroids to facilitate better space travel. Optical mining is the term NASA used to describe extracting materials from asteroids. NASA believes by using propellant derived from asteroids for exploration to the Moon, Mars, and beyond, this could end up saving over $100 billion in cost. If funding and technology come sooner than estimated, asteroid mining might be possible within a decade. Some of these high-value trade goods include precious metals, gemstone, solar cells, ball-bearing semiconductors, and pharmaceuticals. For example, the mining and extraction of metals from a small asteroid the size of 3554 Ammon or 1986 Da, both small near-Earth asteroids, may yield 30 times as much metal as humans have mined throughout history. A metal asteroid this size would be worth approximately $20 trillion. If we were to compare it to 2001 market prices. From a colonization perspective, if we explore history up to this point, the expansion of humans and technological progress has usually resulted in some form of environmental devastation and destruction of ecosystems and their accompanying wildlife. In the past, expansion has often come at the expense of displacing many indigenous peoples, the resulting treatment of these peoples ranging anywhere from encroachment to genocide. Because space has no known life, this need not be a consequence, as some space settlement advocates have pointed out. However, on some bodies of the solar system, there is the potential for extant native life forms, and so the negative consequences of space colonization cannot be dismissed. As mentioned before, another point in support for space colonization is to mitigate the proposed impacts of overpopulation on Earth, such as resource depletion. If the resources of space were open to use and viable life-supporting habitats were built, Earth would no longer be defined by the limitations of growth that it currently experiences. Although many of Earth's resources are non-renewable, off-planet colonies could satisfy the majority of the planet's resource requirements. With the availability of extraterrestrial resources, demand on Earth's resource consumption would decline and allow the Earth to recover. Lastly, from a utilitarian perspective, space colonization should be a chief goal, as it would enable a very large population to live for a very long time, possibly billions of years, which would produce an enormous amount of utility or happiness for future generations. Now, I know you're probably thinking it's too good to be true, because yes, despite the many proponents in favor of space colonization as just discussed, the difficulties are immeasurable, and I'll provide you with 8 clear reasons why. Firstly is the distance, as the distance from Earth to the outer planets is much farther than the distance from Earth to the inner planets, and would therefore be harder and more time-consuming to reach. In addition, return voyages may well be prohibitive considering the time and distance. Imagine leaving and never seeing your loved ones ever again. Think Interstellar. Second, the extreme cold needs to be factored in as temperatures are near absolute zero in many parts of the outer solar system. Third, solar power is many times less concentrated in the outer solar system than in the inner solar system. It is unclear whether it would be usable there, perhaps through the use of concentration mirrors, or whether nuclear power would be necessary. There have also been proposals to use the gravitational potential energy of planets or dwarf planets with moons as a potential source of garnering energy. Fourth is the effects of low gravity on the human body. All moons of the gas giants and all outer dwarf planets have a very low gravity, the highest being Moon Low's gravity at 0.183 grams, which is less than 1/5 of the Earth's gravity. Since the Apollo program, all human crewed spaceflight has been constrained to low Earth orbit, and there has been no opportunity to test the effects of such low gravitational accelerations on the human body. It is speculated, but not confirmed, that the low gravity environments might have very similar effects to long-term exposure and weightlessness. Such effects can be avoided, however, by rotating spacecrafts, which could create artificial gravity. This could be a new mechanism for future spacecraft design. Although probably unexpected, the fifth reason results in space dust that could cause harmful effects on any human outpost technology and crew members. These risks include the darkening of surfaces, leading to a considerable increase in radiative heat transfer, and the abrasive nature of the dust particles may rub and abrade surfaces through friction. There's also the negative effects of lunar dust on coatings used on gaskets to seal equipment from space, optical lenses, solar panels, and windows, as well as wiring. Furthermore, space dust can damage an astronaut's lungs, nervous system, and cardiovascular systems, and the possible increased risk of spacesuit arcing due to small dust grains exposure to the space environment. The sixth difficulty surrounds the planetary protection of other planets humans would look to colonize. Agencies conducting interplanetary missions are guided by COSPAR's planetary protection policies, which dictate that they have at most 300,000 spores on the exterior of the spacecraft, and they should be more thoroughly sterilized if they contact special regions such as water. If more than 300,000 spores occur, this could contaminate life detection experiments or the planet itself. As you can imagine, it is impossible to sterilize human missions to this level, as humans are host to typically 100 trillion microorganisms of thousands of species of the human microbiome, and these cannot be removed if you wish to preserve that human's life. Containment, then, seems to be the only option, but it is a major challenge in the event of a hard landing or crash. There have been several planetary workshops on this issue, but with no final guidelines yet for a way forward. Even worse, human explorers could also inadvertently contaminate Earth if they return to the planet while carrying extraterrestrial microorganisms. The seventh difficulty surrounds the physical and mental health risks to colonists. NASA learned that without gravity, bones lose minerals, causing osteoporosis. Bone density may decrease by 1% per month, which may lead to a greater risk of osteoporosis-related fractures later in life. Fluid shifts towards the head may cause vision problems, and NASA found that isolation in closed environments aboard the International Space Station led to depression, sleep disorders, and diminished personal interactions, likely due to confined spaces and the monotony and boredom of long space flight. Circadian rhythm may also be susceptible to the effects of space life, due to the effects on sleep of disrupted timing of sunset and sunrise. This can lead to exhaustion as well as other sleep problems such as insomnia, which can reduce the space colonist's productivity and lead to mental health disorders. Another problem is the high energy radiation that is a health risk that colonists would face, as radiation in deep space is deadlier than what astronauts now face in low Earth orbit. Metal shielding on space vehicles protects against only 25 to 30% of space radiation, possibly leaving colonists exposed to the other 70% of radiation and its short and long-term health complications. The final difficulty surrounds the premise that space colonization, while often seen as a bold step for humanity, is likely to result in catastrophic outcomes. The potential for creating vast suffering, including extreme forms, may outweigh the perceived benefits. And scholars like Phil Torres and Daniel Dudney argue that expansion into space could escalate perpetual conflict, insecurity, and even increase the risk of human extinction. This aligns with the notion that space expansion amplifies both suffering in non-extinction scenarios and risks tied to advanced AI systems. Furthermore, the astronomical atrocity problem raises ethical concerns about whether positive outcomes can ever justify the immense suffering. Strategic approaches are crucial if inevitable, and space colonization should prioritize compassionate agents to mitigate risks of dystopian outcomes. I want to thank you for taking the time today to cover the reasoning behind why we need to colonize space. Looking forward to discussing more in the next video on space that's coming up next week. I've got some great topics for you. Stay tuned, guys.